Let's get one thing straight. Machine learning models are not magic. They are sophisticated but fundamentally dumb optimization algorithms. They see numbers in a matrix, a high-dimensional vector space, and their job is simply to find a gradient that minimizes some loss function. That's it. Feature engineering is the thankless, brutally critical job of manually manipulating that vector space. It is the act of translating raw, messy real-world data into a clean, well-structured geometric representation that a dumb algorithm can actually work with. It's not art. It's low-level data plumbing. Throwing raw data at a model is like handing a compiler a pile of unsorted ASCII characters. The bottleneck isn't your GPU cycles, it's the quality of the data representation. Raw data is like a heavily fragmented disk. The model has to perform expensive seeks all over the matrix to piece together information, often failing to converge. A well-engineered feature is a direct pointer. It's a pre-computed index that allows the model to jump directly to the relevant sector. It's the difference between a high-speed cache hit and a slow read from spinning rust. We're doing the pre-computation up front so the core algorithm can run efficiently. Here are the fundamental tools of the trade. Don't think of these as a rigid checklist. Think of them as tailored solutions for specific data representation problems you will inevitably encounter. Handling missing data is critical because null values are null pointers that cause training to crash. The fix is patching with mean or median. However, this injects bias and reduces variance. If the missingness itself is a signal, say, a sensor only fails when hot, you must create a binary is missing feature instead of blindly averaging. Binning takes continuous variables and forces them into discrete categories. This allows simple linear models to capture nonlinear relationships, but this is intentional lossy compression. You throw away detail to gain robustness. If the underlying relationship is genuinely smooth, binning will unnecessarily cripple your interpolation capabilities. Categorical data cannot be fed directly, and naive numeric mapping creates a catastrophic false ordinal relationship. One hot encoding solves this by creating an orthogonal representation. The major cost is dimensionality. For high cardinality features like zip codes, OHE is intractable, forcing you to use highly optimized sparse matrices. Algorithms relying on distance or gradient descent are highly scale-sensitive. If one feature ranges up to 1,000,000 and another to 1, the large feature dominates the optimizer. Scaling, either through standardization or normalization, ensures all features speak at the same voltage level, preventing chaotic convergence paths. Scaling comes at the cost of interpretability. Normalization is extremely sensitive to outliers, while standardization assumes a Gaussian distribution. Most importantly, don't apply it blindly. Tree-based models like random forests are insensitive to monotonic transformations, meaning scaling is often unnecessary overhead. Feature engineering is the highest leverage task in applied machine learning. Your model, no matter how complex, is nothing more than a dumb optimization engine operating on geometric principles. If you want high-quality output and predictable performance, you must prioritize the hard, pragmatic work of ensuring your input data representation is impeccably clean.